Well, hi, and welcome to my shop, and thank you so much for joining me. Today is March 25th, and for the last couple weeks or so, I've been working on this radio. I'm right near the completion of it, just waiting for a couple of lights to come today. So this morning, since I can't progress with that radio, I thought I'd go on to the next project and get a head start on it, and that's this radio here. So this is the one we're going to take a look at and check it out, and maybe even operate it. Who knows what we're going to do with this today. So I'm going to leave the big radio just in behind here. I don't think it'll be too much in the way. So let's see. I don't know anything about this radio at all. It's a Marconi radio, AM only. Volume control. Checking to see if there's some gearing in here, but there isn't. This is almost certainly direct drive to the capacitor inside. Looking at the case here, a little bit oxidated. Wow. So this is bakelite. I'm pretty sure you can tell from the color and the pattern. You can see through here, but it's a little hard to see. Especially in the top here, it's so oxidated. Now, there are ways to clean this and bring it back. I have no experience in actually doing that. All I do with bakelite radios is wash them with some water. I don't do too much more to them, but there are techniques, and I'm sure there's lots of information on the internet if you want to try to really bring one of these back. All I would say is you have to be very careful to not accidentally remove a thin surface layer that's on here and reveal some of the filler that's inside the plastic. So a little too much vigorousness on it, and you can kind of ruin it. Let's look at the back here. Vigorousness. So interesting. Phono input. That's a little surprising on a little radio like this. Warning, any person installing or operating this receiving set without first having obtained a license from the Ministry of Transport of Canada is liable upon summary conviction to a fine not exceeding $25, and the said receiving set may be forfeited to Her Majesty. Now that's interesting. That gives you an idea of the date here, because almost always it says His Majesty here, but this says Her Majesty, so it must have been Queen Elizabeth. She probably just became the Queen, by order of the minister, for such disposition as the minister may direct. Guarantee notice. Guarantee under which this radio is sold does not provide for free installation or any service outside of the dealer's store. It must be returned to the dealer for free service within the guarantee, and the dealers are requested to make a service charge for all outside calls. Well, that's kind of interesting. Dealers are requested to make a service charge for all outside calls. That's a weird thing to write on the back of a radio, isn't it? Okay, if you're licensed in Canada under patents, Canadian Marconi Company, Vancouver, Montreal, Halifax, Toronto, St. John's, and Winnipeg. I guess that's where all their factories were at that time. Okay, tube layout is the usual tubes: 12 AV6, 12 BE6, 12 BA6, 50 L6, and a 35 W4. There's a model number 339. Tubes. Use only Marconi RVC radiotrons when replacing defective tubes. RVC. Royal, I don't know, RVC. Don't know what that is. Well, there we are. And down here's another. This is probably the number of this page. Caution, disconnect power cord from outlet before removing chassis from cabinet. I did that. Well, I'm tempted to just plug it in and see what it does, but I think we can go to the next step and just take it out and look at it before I turn it on. But I'm not too afraid to turn this guy on. You got to bet this cord is not the original. It's too short, so I don't think this is the original cord. It's old. Old cord. This is Looks like it's probably, there's one screw here. One screw holding this. Probably to an arm coming up off the chassis. Why don't we tighten that just a little bit? Just to stop the floppiness. So it would be there's no need. It's not even wise to undo the screw here. Just tighten up a little bit. That's better. What we want to do is get the radio out of the cabinet. Where's the screws? Oh my gosh. Okay, so if you notice these corners are cut out. Now, why are they cut out? Because there's a screw right there and right there. And the screw is going into some of the bakelite on the outside. You can see also there's a clip here and another clip here. It's supposed to be holding this back. This corner is broken away. This one's still intact, but it's not being held by the clip. Okay, so we'll take these out. You can tell it's a Canadian-built radio because it's using square head Roberts screws. Square. So I don't think there's too many places in the world where you find these kinds of screws or screwdrivers. Might be a couple countries. I think China was considering for a while making the Roberts screw its national screw, but I don't think they did. But if you're in Canada, the pieces of furniture and anything that's manufactured very often has Roberts screws and very seldom has a Phillips screw or star type screw. I guess we gotta pull this off. We like the Roberts. The radio's on the move. You can see a line up through here. Looks like a crack, but I don't think it is. Okay. Out you come. Dusty, dirty radio. There we go. Antenna wires broken off inside. So we already know this radio is not going to work because of a little broken piece of wire. Let's just make this a little more steady here. And a broken wire right here. I don't think it's supposed to hang like that. So the other wire's heading to the chassis here. This one must be coming to the capacitor somewhere. See where it wants to go naturally. Doesn't seem to want to go anywhere. Quite often a wire like that would be connected to the capacitor here. This is the oscillator section. There's a little piece of wire here. How did it get bent like this? So you can kind of see that. Yeah, probably went just like that. And we do have a phono input here. Again, it's very surprising. This kind of radio, 5-tube radio, no power supply transformer. I'd be pretty hesitant to use it as a amplifier, like for Bluetooth or something like that. I'd be just hesitant about it. These two screws are not identical. They came out of the back here, or out of here, or out of somewhere. Okay. Well, I think it's such a good guess that the wire goes here. I'm gonna solder it here, and then we're gonna turn on the radio and see if it works. See if the antennas come off its glue here. Yeah, see, this wire probably broke because the antenna's been loose and been wobbling around. It just bent this enough to break it off. It's a little hard to believe, but okay, let's solder that back on. So I don't know what's happened here. It's towards the end of March. The weather should be more spring-like, but it's 0 degrees out. Snowing yesterday and today. Not a lot of snow, but just enough. Just enough to keep you aware that it's still winter here. Those sounds you hear are my cats. I'm playing with a couple of bags in the room next to me for the last hour. Not going on very good. Let's go through the hole here. Okay. On. Now when I start this up, I have a way. I have a way of like there's a possibility there's a short circuit in this radio. Who knows? So if you plug it in and turn it on, you're turning on a short circuit right onto your house electric system. It's not really the best thing to do. So what I do when I'm going to start something like this up, where's the other knob? This is the other knob. What did I do here? Okay, well we have a knob missing, but it doesn't really matter because we can do this. And this is really quite hard to turn. So I'm going to lubricate this right away. WD-40 is to some degree kind of a temporary. It's not the best, but you know, it should feel nice and smooth, right? But it feels all lumpy, bumpy. Hey, there's ball bearings in the back here. Is there? No. Getting a little better. Yeah, all that noise is cats. The bumpiness in the turning of this, probably from dried lubrication in amongst the ball bearings. The ball bearings are rolling over top of this dried stuff because now it's getting much smoother, much better. Okay, that's good. Now, here in my shop, it's not the easiest thing for a radio to pick up an AM signal. So I may augment the signal coming to the radio if it doesn't pick up anything to start with. So this box is powered, is for my projects on the bench here. And I control the power coming to this box with a couple switches. And there's so many. I have so many new subscribers. I have to explain a few things here at the start that just may not be familiar with this. Overly fancy looking panel here is just two switches. This one turns the power on. This one directs the power. If I flip it down, directs the power to this outlet and to the project through these lights here. If I flip it up, the power just goes straight from the nuclear power generator, not too far from here, straight into the radio. So through the lights or not through the lights. That's called the dim bulb. system, although, you know, system is way too strong of a word. I didn't straighten my shop up enough here this morning. So, what we're going to do first, a little bit of practice. On, off. So the switch is off. And we're tuned, capacitor closed, we're in the low end. Okay, so nothing should happen because the switch is off. So we're checking the switch. The switch does work. Okay, we're going to switch it on. There's no light in this radio or anything to indicate it's operating except the heaters themselves and whatever sound comes out of the speaker. Now what's possible here? It hit the power and immediately hits humming. Hit the power, it warms up a bit and starts humming. Hit the power, works. Hit the power, nothing happens. All those are possibilities. Okay, here we go. Switch is on. Volume's turned up a bit. Cats are just going crazy behind me here. Here we go. Should have explained these lights better, but they're behaving just the way you would want if everything's normal with this radio. You can see the output tube here is glowing nicely here. So we're in a bit of business, supplying 105 volts. Even though there's light bulbs in the circuit, the current draw is so low, there's not much voltage drop there. And we're left with 106, which is more than enough to operate this radio. Oh, the sound has come. Got a bit of a hum buzz to it. Hum. But I think it's working. Volume control's a little dirty. And there you are. I didn't even look underneath the chassis to see what's been done before I turned it on. So of course Canada's going straight into a federal election right now. The campaigning has started. So this is there's a couple possibilities here. One is the plates are chafing, they're rubbing these plates. Another one is the way in which the capacitor rotor is grounding is not working well, and that's a good possibility. And another one is that's pretty much it right there. So first we'll try the grounding deal here. So the rotating shaft on these capacitors is actually grounded. In some radios grounded essentially to the chassis, but certainly grounded to the frame of the capacitor. Different radios, they treat this a little bit differently, but the rotors are grounded. It's the stators that are actually insulated. See? So the problem is the grounding of these can be wonky because they're rotating, so they have to have some kind of a sliding contact to maintain the ground on these. They can't just rely on the ball bearings in here, or they don't rely on the ball bearings here. So almost always I have a spring or a bent piece of copper or some spring-loaded system that's rubbing on the usually on the shaft itself. If we look here, my gosh, the cats are just not stopping at all back there. So this piece here is part of the rotor, rotates with the rotor. And if you could ground this better, that would be good. And what they've got in this radio is this plate here, which might be very hard to see on the camera, but there's a plate. You could think of it as a piece of metal that's been folded over and shoved down onto this piece here, and then the metal wants to spring out a bit. And in springing out, it's contacting the inside of this rotor here on both sides. And that could be, that contact could be bad. So we're going to hit it with, I tossed a little WD-40 on it. We're going to use this deoxit stuff, which I've commented on before. On the other side. Now usually if it's the plates are shorting out themselves, usually the radio will cut right off. You'll and be right off because the contact is light at first, and then finally it's hard enough to actually. That's not what's going on here. That's weird. Something just made it go louder here. Don't want to do that. Don't want to do that. Too hot. But these ones are the radio tubes, and a little bit of resistance in the socket. The tube will behave very differently. Okay, we got rid of all that. Or did we? Ooh, what was that? Push down hard. Something happened. Didn't sound good. Don't push down hard. What's that? There's jumping again. Volume control, I think. Okay, so we're going to turn the radio over and look underneath it. I'm going to switch it off. I'm doing that so it can sit on these surfaces here. I can flip this, so this radio I can flip right over. It shouldn't really be a problem. It's very light. What do we see inside here? Okay. So one of the things I see right away is this black tape and a capacitor sitting here. Black tape is not something you would find from the 1950s. So probably that's come later, and quite probably this has come later also. This capacitor is probably a replacement. See, there's a two-part capacitor here, this one, and it looks, well, it could be original or it could be a replacement. It's screwed in. The bracket is screwed in, so that would suggest it's a replacement. These brackets that hold these capacitors are often, maybe you can see the screw there, they're often riveted in. So what about the rest of the capacitors? They're all Hunt's capacitors. They're all the same. Probably original. There's not many of them. We've got a resistor over here that appears to have overheated. Let me grab my other camera here if I can just figure out where it is. Where is it? It's got to be over here. There it is. So let's take a look at this resistor here. There's an interesting effect here. You can see the dust that's built up on these red wires, and that's an evidence of high voltage. The high voltage on these wires, on the outside of them, has attracted that dust. Look at the solder job on that connection. It does not look like something that happens in a factory. Oh, that's because that's the lead wire. I was thinking, I was really paying attention to this capacitor, but actually it's a new lead wire somebody soldered in there. A new plug, a new outlet plug. Now the resistor I'm concerned about is this one, right under here. If you look at the chassis below it, and if you look at the wire contact point, is anybody going to tell me that resistor didn't get hot? That is a one hot resistor. So what it's doing there, we don't know offhand. It doesn't look like a particularly high wattage resistor, but it's definitely overheated. What else could we find? And I had this thing playing too with that in it. So down here is one of these packages that contains a couple resistors and capacitors. You can see the leads coming out the top there. 1, 2, 3, 4, 5 of them. You can see. Look at the one there with all the dust on it. That's a high voltage lead. The other ones are not. those cats doing? So Hunt's capacitors, they don't have a good reputation. You know, to be realistic, any capacitor made in the 50s, you got to wonder, here it is in the 70 years later, any capacitor that can survive. They look okay. So these are plastic covered, what they call molded capacitors. They've built the capacitor like they would normally, but then rather than just have it paper or wax on the outside, they've created a plastic housing. But inside, guess what? It's a paper wax capacitor. Okay, well, I think dealing with this resistor is an important thing. I mean, you look at the chassis, you can see all the black stuff there, heat effects from it. This is probably the rectifier tube. Yeah, I think that's the rectifier tube. So we have a resistor tied to the rectifier tube. What else can we figure out about it offhand? So one side, yeah, my camera focus here. One side's coming across, and we're right on the power line, and the other side is just coming over to a terminal on the tube, all by itself. There's no wire on that terminal. Okay. I'm going to try to dig up a schematic. We'll look the schematic over next and see what we can find from that. Okay, let's take a look, see what we can see here. This is what's on this page. This is a page covering everything. So layout, alignment chart, some notes, and the schematic. And this is that little package I mentioned that had resistors and capacitors. Only capacitors in here. Very small value capacitors. And where's that showing on the schematic? Right in here. Okay, let's read these notes. To reduce the hum encountered in some of the earlier models, the filter resistor R13 has been changed from 1000 ohms to 1000 ohm 1 watt to 2200 ohms 2 watt. This is the resistor I think we found overheated in this radio. I think that's what they're talking about. The filter resistor R13. So there it is, R13. But that's not where it was connected, because the resistor I'm talking about is connected between two pin terminals, and it's this one. This is the one I'm talking about, R12, 47 ohms. Why would this overheat? Too much current going into the radio. All the current in the radio is passing through this resistor, except for the heater currents. So this would all be B+ driven current, excessive B+ driven current. Well, that could be everything from these capacitors leaking, and I don't know if they could leak enough to cause a heating effect here. I mean, eventually, they could short. I mean, obviously, you can get that far with it, but that's not the case. The radio's operating. So we don't know why this overheated necessarily, but it could be just general dilapidation all through here. Or you know what it could be? It could be this. Very interesting. Could be this tube is drawing too much. I'm just taking shots in the dark here. And the reason for that would be leakage through this capacitor here, which is inside the package. Volume control, AVC coming from here. AVC on the first tube, second tube. That's it. The diodes here are being used separately. One is being used for the audio, and the other one's being used for the AVC. I think that's what they're doing here. Otherwise, pretty ordinary looking radio, really. Antenna, everything seems to match the radio I have. Capacitor right across the power line here. And here's a capacitor to the chassis. Or is that what that means? What's this mean? So this probably means to a B- wire running in the set. It would be the same wire as this. And there it is, right there. And then the chassis is isolated by this capacitor. Often there's a resistor involved with this, but I don't see one. Wait a minute, what do we got going on over here? 0.02. And this is the AVC line, so this is the AVC capacitor here. Okay, I think that's seeing enough here. The 47. Why don't we measure the resistance of the overheated resistor and see if it's still 47. Okay, so the black lump on the knocked up carpet out there, oh, there she goes, that's our older cat, Shadow, who's just sitting there growling. And the sounds you hear sounds like paper being shuffled, and that's pretty much exactly what it is. There's two cats. Here comes one. So now it's just one cat making the noise. That's what's going on behind me while I'm working in here. Okay, so we're going to measure the resistance of this resistor, and it's in the circuit, but that's okay because it's not going anywhere. It's hooked up to a tube element on one side, and it doesn't 47 ohms. So resistors, in my experience, they tend to go high, they don't go low. So if something like this starts going high, it's more likely to dissipate more and more heat and get hot. Well, coffee's ready. Okay. $51, $47. Well, it's actually $49 now. $49, 50 ohms. That's pretty close to 47. I don't think that's a problem, oddly enough, even though the resistor looks wrecked. I think what it's showing you is it can take a beating and keep on working. So why the beating? The other idea I had was the possibility of a leak on the capacitor, the grid blocking capacitor on the output tube. The output tube is, where is it? This big one here. It's just buried under this bracket and all these parts. This capacitor appears to be connected to the output tube. And flashlight here. I gotta wonder what is this doing here? Is this a bypass capacitor? I'll have to look at the schematic again. I didn't take note of that. So it's hooked up clearly to that terminal there. Now what terminal is that? So I'm looking for the key so I can count the pins. The key is right there. So this is pin number 8. So this is connected to pin number 8. Let's look back at the schematic again here. Pin number 8. I think that's 8 right there. Yeah, that's 8. And here's the capacitor bypassing this resistor, which is 180 ohms. So we should measure this. And this capacitor, 10. That's a big one. And it's definitely a 10 in there. If the bypass isn't here, I'm not so sure that would cause increased current flow through the tube. It's if this resistor is off, or where's the capacitor here? Oh, right here. This capacitor here. So we have a plate voltage on the plate here, and we don't want it to get onto the grid. So to get to the grid, you have to go through a blocking capacitor. But if this voltage floats high, if it goes positive, then this conduct more and more current, and it could get to the point where it cooks this resistor. That would be my theory on this. So we need to check resistance of this resistor. We can assume the capacitor is good enough to do the job. In terms of cooking up this resistor, I don't see the connection exactly. So this resistor, and then we have to somehow judge this capacitor, and the best way to do that, turn the radio on and measure this voltage right here, see what it is. So good idea. I think I heard the coffee machine go off. I'm going to go get some coffee and take a little break, and then we'll perform those tests on that tube. Okay, let me zoom in on this image a little bit more, because we're really just kind of concerned about this area here. So with the radio off, just practicing, first thing I'm going to want to try to read is think, man, what can't you think? So I didn't drink enough coffee this morning. Yeah, let me look at the schematic here. Get my head straight. So we want to read the potential here on pin 5. That's what we want to do. And also read the potential up here. So we should see 40, 50 volts, something like that here. And here we should see 0 relative to the B minus wire. My meter negative is connected to this wire. It's not on the chassis. It's connected here. And we should also read this. Voltage dropping across this resistor is the bias setup on the tube. Okay, we have to go back to practicing here. So reading the bias here is a matter of this it's not making sense to me. What's going on with this resistor here? It's connected here to ground, and that makes sense with the schematic. The other end is connected to a pin and nothing else. Is that right? And the pin would be number 1, 2, 3, 4, 5. Pin 5. So here's pin 5. Well, the nothing else, I'm having trouble here. The nothing else, it's connected up this way. Pin 5 is a grid. It can't just be connected here. I must be not seeing it. How can this be? I'm going to switch cameras here. So you see the resistor connected to this pin here. You know, I'm going to freeze the focus on this camera, or it's going to drive us nuts here. So just bear with me a moment while I do this. I'm just calling up the dialog box for the camera itself, and I'm just going to turn off the automatic focus and maybe bring it in just a wee bit. Okay, now we're operating. See, it comes over to the lead wire to the power cord wire. The other terminal. Listen to those cats. You gotta wonder what they're doing. I sure wonder. I'm afraid to go look. So I'm looking from different angles here. This can't be the case. There has to be another wire on that terminal. Sure as heck don't see anything. Okay, just to be clear what I'm doing here, I'm following the lead coming off of this resistor up onto that terminal. And that terminal is, counting, maybe I counted them wrong? Starting here with 1, 2, 3, 4, 5. 5. What? Okay, let's go back to looking at the schematic here. Something weird is going on. Pin 5. Resistor to ground. No other connection. Am I not looking? You know what? I'm not looking at the 50. I'm not looking at the right tube. What a dork. Yes, I can be a dork. I'm looking at this tube. I stopped looking at the rough. Holy smokes, man. What is going on? My cats are drifting in the hall here. Okay. What are you guys doing? What's up? He went by a little too fast for you there, didn't he? Well, they're off to do their thing. Whatever it is they're doing. I'll just, repair the damage later this morning. Okay. Good thing I practiced this stuff, eh? Okay, so now we're looking at the right tube and can't see anything. So we want to find pin 5 on this tube here that I cannot see much of anything of. Pin 5. So 8, 7, 6, 5. Okay, that's pin 5 there, eh? Pin 5 has a 470K resistor on it, and I think that matches the schematic. Yep, that matches, so that's definitely it. So with the radio operating, I would check here, and we get the grid voltage on the output tube. And then I want to check on the plate side, just for interest's sake, on this other totally. It's just all stuff everywhere. You're supposed to figure that out. Okay, looking at the schematic again. So if we come back here, it's pin 7. We want to get pin 7 or terminal number 5 on this package, but I don't think they're numbered, and I couldn't see them. Sometimes these are numbered, actually. No, I can't read any numbers anyway. So we'll find pin 7 and trace back. Should find a 220K resistor there also. So pin 7. And why did I jump to this tube? Because that's where the package is. And I think that is the correct tube. Pin 7. So 8, 7. So here's pin 7. Pin 7 is connected to a IF transformer. And looking up at the schematic, pin 7. No, 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 no. No, I got the wrong tube, I think. Well, there's a tube diagram, tube layout diagram here. I don't even have to think about it. So we're looking for it. Well, there it is. This is the one I'm looking at. We do have the right tube. Doesn't quite make sense. Diode detector, AVC audio amp. This is the one. So the plate of this tube has a capacitor that blocks its B plus from getting to the grid of going the wrong way. This tube. And that's what I want to test. Okay, so plate is on 12, AV6 on 7. Isn't that right? 7. Okay, so that's easy. That's easy. It's right here. Okay, I'm ready. Ready enough anyway. Here we go. We're going to start the radio up. Good, everything's safe. We're about the ground connection. So the only ground connection I have is I have the voltmeter connected to the B minus line. Okay, just something to keep in mind. Here we go. First interest, we could do this in the meantime. We can check the B plus on in the radio here. That's going to be showing up here. 106 volts on the radio. Let's do this. B plus. It's 150 volts, full scale, just over 100 volts. A little lower here. Okay, grid potential of the output tube. You can turn this down. Notice you can't get rid of the sound. Right, so I got pin 5. Pin 5 of the output tube. Counting again. 8, 7, 6, 5. This is pin 5. What we're expecting here, by the way, would be a negative voltage. So I've switched my meter to negative, so if it goes upscale, it's reading a negative voltage. Actually, we should be seeing 0. In fact, it should be 0. I'm wrong in what I just said. So I'm going to flip this back to positive. It's either 0 or it's going to be pushed positive by a leak. Okay, let's find out. Wow, there's almost a short in there. Holy smokes. Oh my gosh, that's really close. Okay, don't push on that wire. Did we see any movement here? I want to put my hand in front of the... I didn't see any movement in this meter at all. That's surprising. Let's try again. Maybe here. What I hit there? I was looking, I have to look away from the project to look at the meter, and then something happened while I'm looking away. Oh, wow. What did I hit there? Oh, I'm touching the wire that's almost shorting, and I think as I touch it, I'm causing it to short. Let me show you what I'm talking about here. too hard to see in a camera. There's a fair bit of bare wire in here where you wouldn't really want bare wires running. So coming out of the package here is a bunch of bare wires. You see this one going across here? Well, right here, it's almost in contact with that terminal. I mean, it virtually is. And that's the wire I'm testing on. So I touched it with my voltmeter. I believe I pushed it down, you know, some tiny amount. Careful, Jim, you stick your hand in a live radio here. So we're going to have to pull that away from that spot. Where's my little pliers? Okay, made a little video error there. So I don't know how much what you saw. I had to cut out a chunk. I had the wrong camera going. So I found a wire that was nearly shorted, and I was accidentally shorting it when I was taking these tests, and it was causing the meter to give these huge readings. But I've cleared the short now. It won't happen. And when I take the test, and this is the grid potential relative to B minus on the grid of the output tube. We're set here to positive voltage goes up. There we go again. Nothing happening there. Can't even see the pointer move. Well, that's a really good sign. Let's flip this way up again and just make sure the meter's working just by touching this. Yeah. Okay. Well, there's no positive voltage building up on the grid of the output tube. The output tube cannot explain why this resistor is hot. I don't think this resistor is hot. I don't feel any heat. Well, I do feel some heat, but it could be from the socket. So we're going to investigate how hot this resistor is getting. Okay, so this is a thermal viewer here. It's a little hard to see in the camera. We'll give it a try. Now, the colors that are shown on the screen are based on some settings. And right now, let's see, we're going to set this a little higher here. There we go. You see the red stuff is disappearing from view. If you can see that. What it means is red indicates a higher temperature, what I was just doing. So my machine here shows you the temp, this big number here, the 26, 21. That's showing the temperature right under the plus sign in the middle. So wherever you manage to get that plus sign under, it tells you the temperature. And then it also detects the highest and lowest temperature on the screen, and it writes those numbers here. So right now, just looking at the radio, the highest temperature is 36 that you can see. Let's bring that resistor into view. 60 degrees. Now, is that really the resistor though? There's the tube sitting right there. I'm just looking for a blocking, a piece of paper for blocking. This will do. So because of the wide angle on this viewer, it's easy to think you're looking at something, you're looking at something else. So what I'm going to do is I'm going to try to block the resistor, and you can see the block coming in, so you can tell what I'm blocking the resistor. So now you know that red thing I just uncovered is the resistor. And what is the temperature of the resistor? 50, 57, not even 60. So those are low temperatures from an electronic component point of view. It'd be hot to our finger, but it's not hot enough. It's not hot enough to explain why it looks like that. So we could conclude that something happened in the past with this radio, and then something was done about it. That's, you know, what? It could be everything from a tube shorted out inside. I mean, that's possible. The other test is the smell test. There's no particular burning odor coming out of this radio either. So I think this must have been a momentary thing. I mean, maybe not. Maybe at this temperature over a long period of time it can melt into this wire. I don't think so though. There's another interesting capacitor in here I'm going to show you, and it's I'm going to turn the radio off while I do this. We're going to switch to the other camera again. So what caught my eye here was the strange wire to start with. Okay, so we're looking this one. This one right here. Why is it flat like that? If you follow it, it comes down to this capacitor. Now, it's a little hard to see, but the capacitor, half of it is inside the chassis. The other half is outside the chassis above. It's pushed through this hole here. The other part, I don't know if we can really see it. Can we see it here? Yeah, there it is coming through. Now, you know, offhand I'd say, wow, it's just, that's where they put the capacitor. But I think there's a real reason for why this is done like this, with half the capacitor below and the other half above. And I couldn't tell you what the reason is, but I'm very suspicious. And the broad flat lead is kind of weird. So there's definitely something weird about this component. Maybe we can find it on the schematic. Well, we can find it on the schematic. See what it says. What about the rest of my experimenting? What was it I was... So we didn't find any leak to the grid, so there wasn't much more to investigate there, especially with the radio operating. We didn't check the bias voltage. So, okay, let's do that. I meant to do that. Turn the radio back on. So the bias voltage, and you don't have the schematic on the screen anymore. The bias voltage, we should see it on pin 8 relative to B minus. We should get a positive reading on pin 8, not the rectifier, Jim. Don't get confused again. Pin 8. Pin 8. Okay, here goes pin 8. Let me get the probe on it, then I'll move my arm away. Okay. Oh, don't. Stand still, will you? Let me just see if I can't just stabilize this a little bit better. Okay, holding my probe hand in there, and the reading is the meter set wrong. Okay. So we're expecting just a few volts there. Here we go again. I have to count it. Okay, so what happened there? So what happened was you may not have seen it. The meter went right over. Okay, and then I had to yank this probe out, and this probe has a on the edge of it there. It has this funny slice here, which I think is is designed to catch the edge of things like this, so you can do that. Because it's so hard to hold this on sometimes. And as I was pulling it out, this caught something and pulled the whole radio. That's what happened. Accident analysis. Okay, so now we got this set up at a higher voltage, and this time I'm going to try to use... You know what I'm going to do? I'm going to move the meter. Move the camera. Help me. Is it getting late? Not enough coffee? What's going on? How come you're like this, man? Okay. Ready now. We're on the 50 volt scale here. And that the guy there? I can't now because I've changed position here. I can't see this the same way I was. Let me just make absolutely sure. Yeah. Okay, this is the guy here. Let's go down scale. Back in. A little awkward in here. There we are. Oh, for crying out loud. What's that hum? Is that my furnace? Okay, I finally got it there. So we're on the 15 volt scale. This is like 5 volts negative. It sounds a little low to me, 5 volts, but what we will do, did I absolutely read this correct? Yes, 15, 5. We'll look in the book, see what the book recommends for, I think it's more like 15 volts, 50L6. So a low bias would cause the tube to conduct heavily and potentially cook this little resistor. 50L6, typical operation, just grid voltage. Okay, so -7 is the grid potential recommended here for fixed bias, but we're using cathode bias. Under cathode bias, all they're going to do is give us the resistor value. The resistor value would be 180 ohms. So yeah, so the reading is similar to the -7. I would rather it was like -9 or something, but we've also tested the. Did we test the? We actually didn't test the resistor value, and we have the bypass capacitor. I don't think there's any problem in this area. I think I'm beating my head against the wall. I don't think there's anything going wrong with the output tube. Is there anything going wrong with this radio at all? Well, isn't that a good question? And at this point, there's a good question as to whether I should do anything to it, because it all appears to be working pretty well. So I'm going to augment the antenna signal a bit, and then we're going to just run around the dial and see what we can pick up with it. Okay, so just like using these radios in my shop without any antenna help isn't very fair. The antenna help I provided this radio now is actually unfair in the other direction. It's going to make the radio seem better than it really is. So this loop is connected to an outdoor antenna. It's a powered antenna. It's not a wire antenna. It's a mini whip antenna. And so its signal is going to come from the loop into the antenna of the radio itself. And we'll just check this out and see. Are we okay here? Yeah. I have no equipment hooked up to the radio. Other than nothing. I have nothing. The full voltage, 110 volts. I really wonder what have those cats done this morning. That's volume minimum. Maybe a little bit too close. Let's put it here. I'm hoping this big old radio is not intimidating the little guy here. Oh heavens, I let music play. Okay, so I may have got a copyright hit just now, and I may have had to chop that little piece of music out that you wouldn't have heard. That.
Equipment.
We're having an election in Canada and the politicians are trying to hand us money. Elect me, I'll give you this tax break. Elect me, I'll give you that. So you hear that swooshy sound, stuff like. I think that's because of a bad capacitor in the radio. Bad capacitor. And which one would it be? Let's take a look at the schematic and I'll try to point out what capacitor might be responsible for us hearing that heterodyne tone that you could hear. Okay. So one of the challenges in a radio like this is making sure the strong signals down at this end don't find their way back to the front end and start coming through again, or you'll end up with a whistle. That's kind of like the sound we heard just now. So one of the ways that's done is using capacitors connected to the to ground, or in this case to the B- wire, to try to quell those signals so they can't go from the loud end back to the sensitive quiet end. So one of those capacitors is this one. So this is on the AVC line, I'm pretty sure. This is the AVC, yep. Remember how we could hear the radio even with the volume turned to nothing, turned to zero, we could still hear it? Could be that is passing right through this tube here. Because this tube is doing two jobs, and it's got one cathode. And so it's possible if this tube is weak, for that to be the reason why, with the volume down, you can still hear it coming through. I'm not sure that that's true. That's a theory I have. I need to check out. But on a number of these kinds of radios, you can turn the volume right to zero and you still hear it. Annoyingly loud. Like this radio is annoyingly loud. You can't turn the volume down on it. So we could experiment with that at some point. But getting back to the issue of the heterodyne tones. So we got this capacitor. Now there's probably another one. If we look on the screen circuit here. What are you guys doing out there? And I don't expect an answer. So follow the screen circuit back. We should find a big capacitor on here somewhere. There is not one. Well, we get over to here. So it's just relying on this. That's not very good to rely on. Really, there is not a capacitor on this line. So sometimes they use like a common screen circuit through some of these tubes. They haven't done that here. Each tube has its own screen circuit. So maybe because it's not a common screen circuit, we don't have to worry about this signal getting back. I just noticed something kind of interesting. Look at this little piece here. So this may actually be a piece of wire sticking out somewhere in the radio close to this coil. It may be wrapped around the coil. It's hard to say what this is exactly. But look, it's an open wire. Kind of interesting. This is the kind of thing that if you discover it in the radio and you're not familiar with what you're doing, where we are, you might misinterpret what this is. This particular one, I think, is actually a coil wound around here, so I don't think you can misinterpret it. But it's interesting that it's open-ended. That's unusual. So there really isn't a silencer on here, other than this one. And this is going right to the grids. So if there's any signal coming back on this line, I mean, it's going right to the most sensitive grids. So why don't we go after this guy, C9. Now I think we got a part diagram here. Do we? No, we don't. C9. So C9. So this can be in quite a few places in the radio. It'd be tricky to find. It's a .02 going to ground, and it's off of this line here. Okay, I'm going to try to find C9. Good luck to me. Okay, wasn't too hard to find the capacitor in question. It's this brown one down here. But I'm going to use the other camera and show you a close look at it. Okay. So there it is. You see the big crack? The whole end is cracked off. So a crack like that is going to allow moisture to penetrate into the capacitor. It's not a good thing. Well, why did it crack? Who knows? Could be stresses in the plastic right from manufacturer, and it just over time just slowly cracked itself. So that guy's got to be changed for sure, and that is the AVC capacitor, especially if it says .02. Can we see that on it somewhere? No, it's probably buried in there. Okay, so I'm going to cut that guy out of there, and let's do that right now. Put the plug here, and we'll cut him out. Please. So I use the clip lead to remind me where this component has come from, because I never know what's going to happen. You know, I could have to go and deal with cat barf or something like, who knows, and by the time I get back in here I can't remember anything. So another way is when you cut the component out, you leave a bit of the lead wire behind so you can spot it. That's pretty good too. But this is, you know, this is even better. Now I've got to get that capacitor out of there. So let's take a look at the crack here. Let me use the other camera again. I'm going to take a closer look at the degree of failure that's happened here. I was, for a while, my job at the Toronto Hydro Power Company was a cable failure analyst. Yes, can you believe it? How lucky could I be to get a job like that? And my job was to examine every high voltage cable failure and determine a cause, and then determine an engineering action that might be required afterwards. You know, something we should be doing different or whatever it might be. Change standards, whatever it might be. So we had a cable failure about every 3 days, two to 3 days. So I was a very busy guy. So I'm interested in sticking a screwdriver in there and prying that open, but I want to test this first. But it's cracked all the way around. And is this a .02? A 500 volt. .02, so that's exactly the capacitor size it should be. 500 volt. What's that say there? Huh? Huh? Hum? Does it say hum? Okay, let's put it on the tester and we will find out if this capacitor is good or not. Now this tester I'm going to be using here is vintage, like all my equipment. Virtually all my equipment is vintage stuff. This is intended for testing capacitors in tube type radios, so it performs a test that makes sense for a tube type radio, and that's a high voltage test. In transistorized equipment you don't have anywhere near the kind of voltages you have in these old radios. So okay, so he's on the leads. Now the way this works, because you may be a new viewer, you don't know how this works. So this setting here is set to 50 volts. If you can manage to read it, it says 25, but in fact it's 50 that's going to go on this capacitor. 50 volts DC. When it goes on the capacitor, there'll be some current flow. The reason this is moving, it's a cat doing this. Oh my gosh! What? Look. How am I supposed to deal with this situation now? Oh, you got interested in the. There you are. Kind of a remote way of playing with a cat there. You know what? You can't do this, buddy. I'm in the middle of something. Yeah, he apologized. I'll hang on to the camera here so it doesn't go anywhere. When I hit the switch down here, this will apply the 50 volts to the capacitor, and while the current flows into the capacitor, charging it, the eye will snap closed. It'll only take a fraction of a second. The capacitor will be charged and the eye will open. The degree to which the eye opens is how we judge the capacitor. A brand new capacitor will open quickly and completely all the way up to 450 volts. A typical old radio capacitor like this, sometimes the eye won't even open on 50 volts. 150 volts is usually too much for them. Let's see what happens here. So we're on the 50 volt. If the capacitor is good, this will snap closed and open again right away. Like that. Okay, 150 volts. And then it can't do it. So at 50 volts it looks like a good capacitor, but at 150 it's not. Okay, now is this the cause of our problems? Well, I don't know. The only way to know is to change it. And what is the problem? The problem is the radio has a whistle in it. It's a whistler. Feel like having a little bit of tripod trouble here. There we go. So I will put a new 0.02 capacitor in here. We'll play the radio. We'll see if that funny tone has gone away, the heterodyne tone, and then that'll be it for today. Okay, so I got to get a capacitor and stick it in there. Okay, I think we're ready for another try. Got the nice yellow capacitor in there now. Ooh, smoky in here. I must have hit something rubber there with my soldering iron. So, is this going to make a difference? Well, I don't know for sure. I think I'd say 50-50. 50-50. Okay, plug it in here. All ready? Yes. Dim bulbs first. And nothing showed up at all. Because it's not turned on. That's why. Okay, watching the dim bulbs now. Perfect. So they come on quickly because the current rushes into the cold tube heaters. And then the heaters heat up quite quickly and then the current goes down. And the current will rise up again once the high voltage develops and the tubes are all hot. Current starts flowing in every tube and that increases the flow and should cause the light to come on ever so slightly. But this is a small radio, so it's probably not enough to see. Okay, here we go. 105 volts on the radio. Does it still make that sound? Does it still work? So I don't hear it there. Now that's an interfering signal, external to the radio.
Everybody is listening to this right now. Call me when it counts.
So I'd say it's gone. Ooh, what's that? That's interference. Is it? I never heard anything like that before.
and the second with the tax increase on top.
Okay, so tomorrow we will look into this other weird thing. I don't know what that was. That's a strange thing. It's got to be something about the radio, I think. Maybe we can figure out what it is and get rid of it. And another thing is aligning the radio. I could probably benefit from a little touch-up in the alignment, although it does seem to be working fairly well. Okay, that was fun. We'll just carry on tomorrow. Thanks so much for watching my video, and we'll see you on the next one tomorrow. Ciao.